All right, guys, welcome back. We are now continuing our discussion about BGP. This is our second topic of BGP. And in this case, actually our third topic of BGP, we're going to be talking about iBGP versus eBGP and some of the basic peering rules that we need to be familiar with when we're dealing with establishing iBGP and eBGP peers. There's basically three major differences between establishing adjacencies between iBGP routers and eBGP routers. And we'll go through this and kind of expand on our topology. This is the topology that we're using to demonstrate these concepts. I did add another link here for demonstration purposes for later today. I'll save this in the folder. I'll export this file so that you guys can pull this up and practice if you want. We will be adding some of these other routers later on. For now, we're going to focus on R4, R5, and R2 in this lesson. And then as we get into some more of the advanced discussions, we'll add some more routers and continue building on our topology here. But this is what we're going to be looking at primarily in our discussion today. So we're going to talk about iBGP versus eBGP peering rules. Like, what are the loop prevention mechanisms? One of the major differences. How do we do next hop processing? And why do we specifically care about the next hop, and so on. All right. Ultimately, that next hop is one of the major attributes. There's really only about three major attributes that are used with BGP to make routing decisions, or at least to kick off that route recursion process, going from the BGP process into the IGP process. Ultimately, the next hop is what's going to be used for forwarding the traffic. All right, we're also going to take a look at iBGP versus eBGP transport establishment differences as well. That's the third and final thing. That's actually the first thing we're going to look at in our lesson today. So those are the three major differences between establishing eBGP peers and iBGP peers. It has to do with loop prevention. How do we establish a loop prevention mechanism? What do we do with next hop processing? And how do we establish the transport between the peers themselves? Okay. The next hop processing piece is a little bit more complicated. Loop prevention is pretty straightforward. iBGP loop prevention mechanisms are really simple. Simply don't re-advertise a prefix that I learned from one iBGP peer to another. In eBGP, it's a little bit different with AS path evaluation, but we'll talk about that in a little bit later on. First, let's talk about transport establishment, right? And specifically, how does it differ between iBGP and eBGP? Remember, BGP is not a routing protocol, it's an application. It sits on top of TCP port 179, and we use TCP sessions to be able to establish, essentially, for lack of a better term, adjacencies between BGP peers. So it doesn't have its own transport like your typical IGP protocol. OSPF, protocol 89, EIGRP, protocol 88, and so on. BGP runs on top of IP, but it also runs on top of TCP. One of the major differences between how iBGP operates at the transport, with the transport function versus eBGP, is that we have a default time to live. You guys are probably aware of this from your other lessons in CCNA and CCNP. We have a default time to live value of 255. That implies that the neighbors do not have to be directly connected as long as we have some sort of recursion process or reachability exists with some underlying routing process, right? Could be through some IGP process, or could be static routing, or some redistribution process, but we still have to have IGP reachability. All right. For that reason, iBGP peers will typically be peered via their loopback addresses. We'll actually demonstrate that concept. That'll be kind of one of the last things that we do in this particular lesson. We're going to focus most of our attention on eBGP to start with, but we typically peer with loopbacks, and that's because we may have in the underlying transport many different ways of reaching those iBGP peers, and we want to make sure that we have continued reachability. If a primary path fails, we can use a secondary path. All right. This is actually also going to be required for something like an MPLS layer 3 VPN, and so on. There are some design cases, we don't see it very often, But there are some design cases where BGP could be used as an internal routing protocol. Extremely rare, all right? But there are some design cases where this could be done. We talked about that a little bit in our previous lesson, actually, where you might decide to use BGP as your internal routing protocol if the domain is just too large to scale to some sort of IGP routing process. All right? The limitations of BGP are going to be pretty extensive when it comes to utilizing it as a core IGP as opposed to an inter-AS routing protocol when we're going from one autonomous system to the other. Now, conversely, when we're talking about eBGP transport, the TTL is 1 by default. All right. Now, this implies that the neighbors, doesn't really imply, it actually restricts it, that the neighbors have to be directly connected in order for them to establish an adjacency. Because we cannot route those BGP segments, those TCP segments that are being used to establish the TCP session. Now, this could be modified if the neighbors do happen to be multiple hops away. There's a couple of ways that we can do that modification. I'm going to demonstrate that actually as part of our process here. We're going to take a look at several different configuration scenarios in this case. But again, our focus is on the peering relationship rules. All right, that's all we're going to be talking about. There's going to be plenty of other stuff that we'll be talking about with regard to BGP confederations, route reflectors, BGP design implications, and best practice design scenarios. But our focus is to continue to build on our knowledge of BGP based on the 2 previous lessons that we had before. So we could modify the neighbor limitation, if you will, for BGP. We can use the eBGP multi-hop TTL command. That will simply allow us to change the TTL to a specific value. And I think most of you are probably familiar with that concept. If I want to establish a BGP peering relationship, for example, between router 4 and router 5, using the loopbacks, I would want to use eBGP multi-hop command. It's an interesting concept because we're actually not doing multi-hop routing in that particular case, but BGP at the control plane still considers it to be a multi-hop peering relationship, even though a trace route would indicate that you're only 1 hop away. All right, we'll demonstrate that a little bit later on as well. So the eBGP multi-hop command, which I will demonstrate, very simple. We're just setting a TTL value to a specific value for that peering relationship, and as long as we maintain a time to live underneath that value, so if we set it to 3 and we're 2 hops away, if we set it to 5 and we're 4 hops away, we'll be able to establish a peering relationship between those 2 peers up to 255 hops away. The other one, though, is called the neighbor TTL-security hops TTL command. Since you probably haven't seen that one before, let me go ahead and just throw that into Notepad here. We'll demonstrate this as well. And I'm going to talk about the difference. These are mutually exclusive commands. You can't use them both together. You would choose to use one or the other, not typically both. So TTL security hops, and then we would specify some sort of TTL value. This is different than doing the neighbor eBGP multi-hop command. And we would specify some sort of TTL value. Remember, you're still going to specify the neighbor itself as well, referencing the peering address that you're using for that particular neighbor. All right. Now, the first option that you see here, this TTL security option, that's a better implementation for current designs, specifically for control plane security. It's something that we would typically implement instead of just doing a standard eBGP multi-hop configuration. Like I said, I'm going to demonstrate this and I'll talk about the implications. It's a little bit counter opposed to what the second command is. Second command essentially specifies the maximum number of hops that the peer can be away from me for me to be able to establish an adjacency, whereas the first command specifies really essentially the minimum number of hops. And I'll explain what I mean by that as I go through the demonstration. All right. In addition, typically when you're running any kind of routing process, specifically BGP, you're going to want to run some sort of other security implications, right? You want to do some sort of authentication between the peers. The reason why you don't want to strictly rely on authentication, though, is because you can actually open yourself up to a DOS attack by only configuring authentication and then just setting the TTL eBGP multi-hop command, right? There are some attacks that you can actually do against BGP based on guessing TCP sequence numbers. We'll talk about that in a little bit, but why would I be concerned about the authentication? All right. Well, if I'm running purely authentication, to authenticate peers, I can just simply send a bunch of datagrams to a BGP peer and I can overload the control plane because the BGP process is going to have to verify that information against the hash that's being generated for the authentication process. So it could just be a matter of overwhelming the router with this cryptographic process. All right. The reason why we would typically want to provide some sort of authentication and at least have some sort of security implemented, whether we're doing TTL security hops or we're doing authentication or we're doing both, is because it is a TCP-based application. All right. So I could essentially do some sort of TCP reset DOS attack against a peer by simply sending in a whole bunch of TCP resets to random port numbers, and eventually I might be able to guess the TCP sequence number, which would cause some sort of TCP reset, and eventually we would drop the sessions and drop the routes, and that would eventually result in some sort of attack against the data plane. All right. We could rate limit BGP as well. We can do other things with control plane policing and control plane protection, but if you just implement some very basic security features like neighbor TTL security hops and maybe add some authentication, you can protect against a lot of these different attacks without having to do any additional control plane protection. All right. The idea of doing the TTL security command in this particular case is that when the neighbor checks the packet that comes in, it checks the minimum TTL value. So basically what that indicates is the router has to be a certain number of hops away. All right. I'll explain what I mean by that. But let's say, for example, I've set it the value to 1. Okay. I've set the TTL security maximum hop value to 1. So I've said neighbor TTL security hops 1. That doesn't mean that I have to be 1 hop away. That means that the TTL cannot decrement below 254. That it's specifying a minimum rather than specifying a maximum. I'll demonstrate that, and we'll take a look at that in the packet captures as well and see what that looks like in the packet captures. All right, it's completely the opposite of just doing an eBGP multi-hop command where we're just specifying the maximum number of hops the peer can be away, because in that particular case, the peer could be 5 hops away, it could be 100 hops away, it could be 50 hops away, depending on whatever the TTL value you specify is, which means that you're opening yourself up to potential attacks from all kinds of vectors at any, various distances within the internet or within the routing domain. Okay. So let's go ahead and set up a basic eBGP peering relationship. We're going to do a packet capture between router 4 and router 5. This is, like I said, kind of a continuation of what we did previously in our previous configuration. I'm only going to establish the BGP peering relationship on the 45 link for now. We'll take a look at the cloud link a little bit later on, but we'll focus on the 45 link in this particular case. What we're simply looking at in this case is how do we see these defaults demonstrated in the packet capture itself. So let's go ahead and start the packet capture on the link here, and we're going to do just a basic BGP peering configuration between router 4 and router 5. Presently we're not running. If I do a show IP protocols, I took off all of the BGP process. I'm only running eIGRP, and that's it. Okay. Now normally you wouldn't run eIGRP between external peers. I'm actually doing that for a different reason, to demonstrate some other concepts a little bit later on. Typically we just rely on some sort of connected routes or static routes, and then we would establish the peering relationship between the peers based on that. All right. So let's go ahead and set up BGP here. So we're going to do a config T, router BGP 4.4, neighbor. In our case, in the initial design, I'm going to continue what we did previously based on our previous exercise. I'm not going to peer to the loopbacks presently. I'm just going to go ahead and peer to the physical interface IPs just so we can see some of the defaults before we start modifying those configurations. So I'm going to say 172.16.45.5 remote AS 5.5. All right. I'll do the same thing on router 5. By the way, we should see in this case, let's go ahead and filter out not selected, and let's filter out not selected, filter out not selected. That should give us pretty close. So we can already see that we're seeing TCP messages going back and forth. We talked about this in our last lesson. I'm getting a TCP reset from router 5 because router 5 is receiving the TCP SYN request going to port 179, but router 5 does not have router 4 configured as a peer. Router 5 actually doesn't even have BGP configured, so it's not listening for the BGP process. All right, so let's go ahead and enable that on router 5. Config T router BGP 5.5 neighbor 172.16.45.4 remote AS 4.4. All right. Now what we should see is we should see that we start to progress through our BGP establishment process. We have direct connection reachability. And as soon as we see this BGP open message, that means that we've essentially established our session. So if I wanted to see what a TCP reset might look like, I can come into the router and do a clear IP BGP star. And we should see a fin sent to the peer indicating, hey, we're trying to close the connection. This is coming from router 5 going to router 4. We're trying to close the connection. We're pushing that through the TCP process. Push flag means let's go ahead and process this packet immediately or this segment immediately. And we can see that the TCP session reset. Okay. Actually, it'll come back up as well because we just cleared the process. So we should get another open. We get our keep alive, and we should see that we've now established the adjacency. Okay. But the fin flag indicated that we were closing the session. After the open, we take a look at the keep alive messages, indicating that we've essentially gone through the process of establishing the session between the BGP peers. What I'm looking for specifically here are the defaults, right? Here's the source port. There's the destination port. So this is a response from the server to the client. That means that the other router is the client in this case because our source port is 179. But the most important component of this particular segment, if you will, is in the packet header, and it's this time to live value. Okay? We haven't actually advertised anything into BGP yet. All we're looking specifically at in this case is the packet header. We see a time to live value of 1. We didn't get to see that last time when we were doing our configuration because my Wireshark capture wasn't working, but we get to see it this time. And that's pretty standard for an eBGP peering relationship. We get a time to live of 1. Okay, now let's go ahead and change this under the eBGP process. We're going to use the multi-hop command. Technically, we really don't need to, but all I'm trying to demonstrate is in the packet capture, we see that reflected in the BGP updates and keep alive messages. So I'm going to do neighbor, in this case 172.16.45.5, and I'm going to say eBGP multi-hop 100. All right, and I could do the same thing on the other side as well. Just to be consistent, router BGP 5.5, neighbor 172.16.45.4, eBGP multi-hop 100. So if I go back to my packet captures now, what I should see in these captures is the reflected change in the keep alive messages as well. All right, let's see, are we still capturing? Should still be capturing. Let's clear the session real quick. Do clear IP BGP star. And we should see it, yeah. So here's keep alive, and time to live is now 100. So it's a very, very simple change. We're simply changing the time to live of the segment, of the packet itself, which carries the segment, we can see the TTL value is now 100. All right, pretty basic concept. That means essentially that these routers could establish a session with each other up to 99 hops away. Anything over 100 hops would be unreachable, and we would not be able to establish the adjacency. All right, now TTL security is completely different. It's basically the reverse logic of what we were doing in this particular case. In this case, we're just saying, look, I can accept messages from you as long as your time to live doesn't exceed 100. So it could be 50, it could be 40, it could be 20, whatever. Any number below 100 is going to be acceptable, which kind of still opens us up to a lot of different attack vectors if we have a relatively high TTL value. All right, now let's go ahead and change this configuration on both routers. I'm going to go into router 4, and I'm going to do neighbor 172.16.45. I might have to take out the other, oh, we're in router 5 right now. I might have to take out the other configuration, but let's go ahead and see if it takes it. Might yell at me. Hops 1. Yeah, so these commands, like I said, are mutually exclusive. They cannot be configured together. The parser is telling me, hey, you've got eBGP multi-hop already configured. You need to remove eBGP multi-hop before you can set up the TTL security. All right, so let's do a no neighbor, and then we'll put in our neighbor security command. Same thing here, do show run section BGP. Take out the multi-hop option. And let's do a neighbor 172.16.45.5, and we'll do Ttl security hops 1. All right. Do a clear IP BGP star. Now, if you were not familiar with this command, you would actually go through and you might take a look at this and say, all right, well, that means that I'm basically saying you can be 1 hop away. Kind of like doing an eBGP multi-hop of 1 or 2 or whatever it might be. But if we go back and look at our captures, go towards the end here, we can see that it's significantly different. In the packet header, the time to live value is set to 255. All right. That doesn't mean that you can be 255 hops away, though. All right, this is very important because in this case, what we're essentially saying is that the router has to be directly connected on the eBGP link. Has to be directly connected. For example, if I was to change the peering address to 4.4.4.4 and 5.5.5.5, which are my loopbacks, the peering relationship would fail because from a control plane perspective, from a BGP perspective, we're more than 1 hop away. All right. The basic logic of this essentially is that I can use the TTL to determine how many routers did this peer go through before it got to me. All right. And in this particular case, it can't go through any routers because we've essentially set the minimum TTL value to 255. Anything below 255 would be considered routed, which means that the packet's going to be denied. All right. We could demonstrate this concept if I come into my router here, do show run pipe section BGP, and I'm going to do a couple of things here. I'm going to show you guys this a little bit later on as well. Let's do no neighbor. There we go. And let's do no neighbor. All right. And yeah, it looks like it took it out anyway. Show run pipe section BGP. We're going to go ahead and set up the peering relationship with router 5 using its loopback. So let's go into in space specify neighbor 5.5.5.5 remote AS 5.5. I'm also going to do a neighbor 5.5.5.5 update source loopback 0, and I'm going to put in the same command I had before with the TTL value of 1. So TTL security value of 1, where it is right here. Let's do neighbor 5.5.5.5 TTL security hops 1. All right. Obviously, I'm going to have to do the same thing over here. It's probably going to be easier if I just do no router BGP 5.5 router BGP 5.5 neighbor 4.4.4.4 remote AS 4.4 neighbor 4.4.4.4 update source loopback 0 and neighbor 4.4. 4.4.4.4 TTL security TTL security hops 1. Okay. So if I do a show run pipe section BGP, the only thing I did here differently is now I'm peering with the loopbacks as opposed to the physical interface. If I do a show IP Ceph 4.4.4.4, I want to make sure I have reachability. I do, and that's because I'm getting reachability through eIGRP. Keep in mind, this would not normally be the case. I would not want to use some sort of IGP protocol between external peers, but we're doing it in this case. All right. But if I do a show IP BGP summary, you can see that the state is never, the up-down state is never, and we're in the idle state. And that's because we're essentially exceeding that time to live parameter. All right. I don't know that we would actually see that in the packets. If I did a trace route to 4.4.4.4, we can see that it's specifying that it's only one hop away. At the data plane, that's true, but at the control plane, it's not true, right? Because we're, from a BGP perspective, we're routing the packet to the loopback at the control plane, and the BGP process is looking at that as a TTL of 2. So if I do a show run section BGP, oh, and by the way, if I come into my packet captures here, I should be able to see, let's see here. Yeah, we're actually not even seeing the datagrams now that I think about it. And that makes sense, actually. Okay, and here's the reason why that makes sense. The BGP process is not going to generate any of these peering, open messages or these TCP connect messages because it already knows that 4.4.4.4 and 5.5.5.5 are not directly connected. So rather than send out TCP send requests that would ultimately get rejected by the peer anyway, we know that we're breaking the rules of our peering agreement because we only have a TTL security maximum hop of 1, so we're not going to even try to establish an adjacency in that particular case. Let's go into our BGP process and let's set the hop limit to 2. Same thing on router 4. And in this case, we should see the adjacency form between the two peers. And we do. All right. But you definitely need to know the difference between TTL security hops versus eBGP multi-hop. All right. Definitely need to know the difference. And by the way, the TTL security command would work with iBGP peers as well. So that's unique to, not specific to eBGP peering relationships. All right. So again, like I said, the basic logic of this, I want to be able to look at the TTL, to determine how many routers I went through, how many routers did the packet forwarding before it got to me. All right. Let's say I'm trying to attack router 5. And I can't insert myself physically into the link, but I'm somewhere in the IP cloud or I'm somewhere on the internet. The first thing I need to do is to spoof R5's address or spoof an address that R5 is supposed to be talking to. That's pretty arbitrary, right? It's kind of trivial to be able to do something like that. I can trace from lots of different points on the internet and look at what addresses show up on the link. We can actually demonstrate this. Let me see if I can pull this up. I haven't tried this, but let's go ahead and see if we can. Let's go into one of our route servers, routeviews.routeviews.org. Is it going to connect? Would have connected if I would have spelled it correctly. RView. I think it's RViews actually. Let's try that again. I'll get there eventually. There we go. All right. So let's do a trace. We're going to do an IPv4 trace to www.cisco.com. So let's say I'm trying to potentially attack, some router along the way or along the path, and I'm trying to essentially enumerate this path that's happening or that's available. We can see it's actually showing us quite a bit of information here. We're seeing the providers that we're going through. We're seeing what the autonomous system numbers are. And we're also seeing the specific addresses of the links themselves. And most of these are going to be probably /32s or /31 types of links. All right. Also, most providers, for the most part, they're not going to filter out ICMP unreachable messages because it simply makes it too difficult to troubleshoot the network. We are actually seeing some filtering happening here, but typically that's not going to be the case. All right. So my point is, I guess, that discovering reachability information is a rather trivial concept. And then, of course, crafting packets using Armitage or, Nessus or something else like that, it's a pretty simple thing to do as well with a spoofed address. All right. So we can discover the addresses, the routers that we're pairing with. We can figure out what address we're going to spoof from. And then we just send a whole bunch of TCP resets to port 179. Eventually, I'd probably find out which particular sequence number is correct, and I'd be able to reset the session in that particular case. Like I said, there are some other mechanisms that we can use to protect against this type of thing happening, but by filtering out what's actually allowed to be accepted by the router will provide an additional level of security. It's not the end-all, be-all. There's still other security mechanisms that we probably need to have in place to ensure that we're completely secure. But this is certainly another layer of security that we can add. All right. Like I said, we don't just want to authenticate a session between the peers. We certainly want to add authentication. That's a component that we typically would like to include, and we're actually going to get into BGP authentication later on when we're going to talk about BGP security. But remember, with authentication, we have to do an MD5 hash, and somebody can DOS the CPU by just sending a whole bunch of malformed frames because we end up having to hash each one of those frames. So in our particular case, well, prior to making this change with the loopbacks, we were directly connected. We're saying that the packet should have a value of 255 because it wasn't routed. We're not saying that it could go up to 255 hops. We're saying essentially that the packet would have to have a TTL of 255. All right. So in our case, any TTL of 254, which was demonstrated by changing it to the loopback, would mean that there were more than one hop away. The packet's ultimately going to get discarded or not being sent at all. All right. So we set the TTL value to the highest possible value, 255, and then we have this lower floor, and I'm basically saying, hey, I am not going to accept any packets to my router below that particular level. All right. All right. In fact, we actually saw that we throw away the packet before the control plane even sees it because we don't even want that packet to get to the general purpose CPU in this particular case. So these are your two options. There is actually another option to disregard the TTL. We'll take a look at that. That'll be one of the third options that we look at when we go into a couple of other choices here in a minute. Okay. They are mutually exclusive commands. You can't use them both. As you saw, the parser complained when I tried to implement both. But technically, like I said, we're not really running multi-hop BGP in this case because we are peering to the loopbacks. All right. Now, in our particular case, you might say, well, why would I want to peer to the loopbacks? If we look at our topology here, it's pretty obvious. Router 4 and router 5 have multiple methods of reaching each other. So peering to a physical interface IP means that we lose that redundant capability between the routers. If the link, 45 link goes down, well, prior to making the change that we made, if that 45 link goes down and that's the link that we're using to peer between the two routers, then guess what's going to happen? We're going to lose our adjacency, even though we have a secondary link that's available to us. This is a very similar concept to what we would see with iBGP as well. In the case of iBGP, oftentimes iBGP peers are not directly connected, and they are reachable through multiple paths, so we would typically want to peer with loopbacks. The only difference with iBGP as opposed to eBGP is that we don't have to worry about a TTL value because the TTL is already going to be 255 by default. All right. Let's take a look at some of the routing here real quick. Even though we've kind of already implemented this, I want to step back a little bit and talk about some of the route recursion. Because this one thing, we're not advertising any prefixes into the routers presently. If I did a show IP route BGP, we don't see any BGP routes, but if I do a show IP BGP, we also don't see anything in our BGP database, our BGP rib, if you will, because we're not advertising prefixes. Remember, we don't enable BGP on links, we enable BGP for prefixes. And presently we're not sending any prefixes in, but we are peering between BGP speakers using those loopbacks. So we need to make sure that we have some sort of recursion for that destination. So if I do a show run section, pipe section BGP, obviously we're peering to the loopbacks. I would want to do a show IP route 4.4.4.4, and in this particular case, we do have two different ways of reaching 4.4.4.4. We're actually using ECMP in this particular case, even though the cloud is just a switch, an Ethernet switch. The router thinks it's a gig connection. So we see that we have through EIGRP 100 that we're learning about this prefix in both ways. If I do a show IP route for my database here, or my rib, I can see that we're load balancing for the 4.4.4 prefix. All right, so we've already set up BGP using those loopbacks, but I didn't quite describe, and I think I did talk about this in the last lesson, one of the commands that I implemented, show section BGP, which was the update source command. By the way, these are the decimal values of the 16-bit ASN as opposed to the 8-bit ASN that we typically would use. It's just being converted to, excuse me, the 32-bit ASN, sorry, as opposed to 16-bit. It's just converting it to a decimal number. We can change that behavior. We looked at that in the last lesson as well, how we can make sure that we're continually using the dot notation as opposed to the decimal notation. I'm not going to change it because we can still reference the configuration using the dot notation, even though it's in the syntax and the parser, it looks like as a decimal notation. So just to make sure that you're aware, in this particular case, We're just looking at the decimal notation of the ASN. All right. So we have neighbor 4.4.4.4, which is the loopback. We already confirmed recursive reachability to that loopback through our IGP process. Normally that would probably be done with some sort of static route. Like I said, we might even have multiple static routes for ECMP, or at least redundancy in routing, not ECMP with static routes, but at least some sort of redundancy. Okay. But the key here is that, of course, if I'm sending a TCP SYN request from one router to the next, I need to make sure that that SYN request that I receive is authorized, right? We're not just opening up port 179 and we're accepting simply every TCP SYN request. We're opening up port 179 and we're accepting a TCP SYN request from our peer, which is pre-configured in our BGP configuration. Because the router always sources the packet from the egress interface IP address, we need to override that behavior by using the update source command. And update source says, hey, if you're going to generate any TCP messages to this peer, go ahead and source those packets or source those segments from your loopback 0 interface. All right. If I did not set the TTL, I'm going to demonstrate this one more time. I want to be very clear about this. So let's say I went kind of back to my default. Do show run section BGP, and I'm just going to take out the TTL Security hops 2. Same thing on router 5. 5.5. And I'm going to clear the adjacency. Do clear IP BGP star. All right. If I go back to my packet capture, you will notice that I'm not receiving. So this is where we cleared the session. And this is where we acknowledge that we're clearing the session. So this is the router 5 telling router 4, hey, I want to kill the session. And I'm not sure what this final acknowledgement is, but anyway. The point is that at this point, we're no longer sending or receiving BGP messages. All right. Again, the router's smart enough to say, hey, based on my local routing table, my local routing database, that address that you specified the peering relationship to is not locally connected to my router. And because my TTL, my max TTL value for eBGP is 1, I know that there's no point in me even sending a TCP SYN request because it's not going to reach there. And even if it does reach there, it's going to get, well, it would probably reach there. But even though it reaches there, it's going to get rejected anyway. Okay. So we do have the right update source. We just have to set the time to live. Now we do have another option here. This was a third option that I was going to mention, which is to do something called a disable connected check. And this is the exact scenario where we might want to do something like this, where we know that we're actually technically not more than one hop away. We're peering with loopbacks. We don't want to set the eBGP multi-hop. We don't want to set the TTL security hop limit. But we want to ensure that the peers can establish an adjacency without using those other two options. So we can go into the routing process. This is something that you may end up having to configure in the lab as well. And we just simply say neighbor 4.4.4.4 in this case, and we're just going to do a disable connected check. We'll do the same thing on, this definitely has to be configured on both sides. Neighbor, because one side would accept the segment, the other side would reject it. Disable connected check. And you'll see what will happen is that these routers will form an adjacency or a TCP session, and they'll connect with each other. Okay. And if we actually go back to the packet capture, we're not overriding the standard eBGP peering rules. The TTL is still going to be 1. Let's go to our keep alive here. The TTL is still going to be 1, but we're not rejecting the datagram, right? And that's what I meant to say in this particular case when I said we're not actually routing, right? Even though the packet is going from 4 to 5, sorry about that. So what I was saying is even though the packet's going from router 4 to 5 and it's going to a loopback, it doesn't decrement the TTL, right? We don't actually decrement the TTL until the packet is forwarded out of a new link. In this case, it's going to a local control plane process. We're not routing to the loopback. It's just a logical construct. That loopback is just a logical construct, so we're just sending it to the BGP code, but BGP still kind of views it as a second hop, if you will. All right? So that's why we would put that particular command in place. All right? Why would we want to peer to the loopback? The result of this is going to be based on the advertisements that we're sending, the next hop value, and so on. We're going to get into next hop in our next discussion. I mean, as part of this discussion, our next component of this discussion, because that's a pretty critical thing when we're talking about iBGP versus eBGP as well. All right. We'll talk about next hop last. Let's talk about the next piece. All right. So the first piece, like we said, is the TTL. That's a major, major consideration. How is the TTL manipulated? How is it controlled? What is the value? What are the defaults based on iBGP versus eBGP? Very important concepts. The next important concept that we're going to talk about, number 2 of 3, is what are the loop prevention mechanisms? All right. In iBGP, like I said, the loop prevention mechanism is really, really simple. If I learn a route from one iBGP peer, I'm never going to send it to another iBGP peer. All right. Now, keep in mind what that means, because there's a few implications with this concept. All right. Number 1, it typically means that the routers either need to be iBGP peers if they need to exchange routing information, they need to be a full mesh, or you have to have some sort of exception, which would be done with either using a route reflector or some sort of confederation configuration. There are pros and cons to all 3 options. There are cases where you may want a full mesh. There are cases where you may only need a confederation or reflection, although I'm going to say most people won't use confederations. Most people will use route reflectors. I don't think confederations are very popular these days. No, not a whole lot of specific use cases for that. Almost everything in that particular case is done with a route reflection. Basically, they're both the same, right? Both of them are used for the same purpose, which is to reduce the need for a full mesh. All right. So it's very simple in iBGP. If I get a route from one iBGP peer through the BGP process, mind you, not through some underlying iBGP or IGP process, but through the iBGP process, I'm simply not going to send that route on to another iBGP peer. Okay? In eBGP, it's a little bit more complicated. We're going to use one of the attributes that are part of the BGP update, which is the AS path attribute. So in order to prevent loops, whenever I send outbound updates, I'm always going to prepend to those outbound updates my ASN. All right, very simple concept. Any inbound update that contains my local ASN means that those routes are being reflected back to me, and I'm going to disregard those routes or discard those routes because there's no reason why I should be seeing my own AS in the AS path because it's, well, it means that I originated that route and somebody has somehow sent it back to me. We can override this behavior. There's a couple of ways. We can do a allow ASN, or what we call an AS override. AS override is a little bit more common, typically with MPLS networks where you've got a bunch of domains that you're connecting, or a bunch of customer sites that you're connecting to an MPLS domain. but you own your own ASN. I'll draw a little diagram here in a second and kind of describe what I mean by that. All right. We're actually going to talk about some of these behaviors. It's a little bit beyond the scope of what we're doing now, but there are some options with BGP optimization where we'll talk about allow ASN or AS override. Typically, AS override is going to be used with a layer 3 MPLS VPN, where the customer is maybe attached to the provider with, let me see if I can kind of draw a diagram here. Let me pull up my handy dandy MS Paint. All right, so let's say in this case we've got our MPLS cloud here. Let's say they're using AS1. And then I've... Sorry?
I don't see that screen. Okay.
You don't see my screen? You can't see me drawing? Can anybody else see me drawing?
Yes, see it.
Okay. You see it, Chris?
No, unless the video just froze or something. No,
Kathy? Now you can see it? Okay.
Yep. A little delayed, I guess.
I can see it.
Okay, you're missing out on my high-tech drawing here. All right.
It's really good now.
It's good. I know. This is like who's that guy who drew the soup cans? One of his paintings sold for like $150 million. All right. So let's say I'm exchanging routes with my MPLS provider, and obviously as I'm sending X into the MPLS cloud, I'm going to prepend the AS to that particular AS path attribute. Now we don't really need to know the specifics about what's happening in the MPLS cloud. We know that we're running some sort of VPN v4 BGP between the PE routers. We'll get into that a little bit later on, but when we get into MPLS. But we're just exchanging prefix reachability information, NLRI, between those PE routers, and eventually that's going to get sent back into CE2. But X, in this case, is going to have 1, 2, 3, 4 as part of the AS path. That's going to be a problem when CE2 sees that information because of the loop prevention mechanisms with eBGP, which says I can't see my own AS in the AS path, and I'm going to reject the route. So we would actually do an AS override, and that's what the override essentially means, is that we're going to go ahead and take this information out. We might put in a 1 or some other information so that when CE2 gets the information, it's not going to see 1, 2, 3, 4 in the AS path properties. All right. We'll talk more about that in more detail when we get into the optimization of BGP, and we'll talk about not only AS override, but we'll also talk about allow ASN and some of the other ways of manipulating different attributes. All right. This is kind of like a hack or a workaround. There is no loop in the process. I mean, technically, we can see that visually here. There's no loop in the process, but BGP doesn't really know that, and we'll replace that AS with our own information. All right. It does fix the problem, by the way, with the loop prevention, but it does make the design a little bit more complicated. There is another feature we could use called SSO or SOO, or site of origin. We'll talk about that in our advanced BGP discussion as well, which is basically like a tag. So we can identify where the traffic is actually coming from. It's called site of origin. All right. The last thing I want to talk about is the next hop significance. And this is a really, really critical concept. So just to recap, we talked about transport limitations or transport differences between iBGP and eBGP, namely the time to live. We talked about the loop prevention mechanisms with iBGP being don't advertise prefixes learned from one iBGP peer to another, or In the case of eBGP, looking for an AS path, a local ASN and the AS path attribute. Now let's talk about next hop. All right. What is the next hop value is going to be advertised in any BGP update. Doesn't matter if it's coming from an iBGP peer or an eBGP peer. This is a well-known mandatory attribute, meaning that it's required by all BGP peers to understand. Everybody does understand it, and everybody has to include this information in their updates. It is actually one of the most important attributes inside of BGP. Remember, and I've said this 1,000 times already, BGP is an application that's used to exchange network layer reachability information. We are advertising the route details, but we're not advertising the path details. Very important concept. In IGP processes, we're advertising path details. We're not advertising route, well, actually, I guess technically we're also advertising route details in that particular case. But those route details include the path details. If you look at a BGP route, it contains basically three things. What is the prefix, right? The x.x.x.x. What is the prefix length? What are the attributes for that prefix, like local preference, multi-exit discriminator, weight, AS path, etc. And lastly, what is the next hop? Now, there could be some other things that might be included. I'm talking specifically about IPv4 unicast, but we could see some other information in other, multicast or v6 information. The next hop value is extremely critical because that's what BGP uses in the process of route recursion to find the actual outgoing interface of a prefix. You have to use some sort of IGP process to perform recursion, otherwise the route cannot be used. Let me show you what I mean by that real quick. So right now in our topology, we're not really advertising any links here. I'm going to go ahead and set up a link between, creating a link on that port is not available. All right, let's try this. Let's go 02 to 02 in this case. And this link is going to be 172.16.57.0/24. I'm not going to run BGP here. It's just going to be a connected interface. So I'm just going to go into router 5 and turn that link on. We'll set this link up a little bit later on. But let's just go into router 5. Now I've already forgotten what interface that was. 02? Yeah, 02. Okay. 57. All right, interface gig 02. 172.16.57. This is router 5. And we'll just do a no shut. Do show IP interface brief. And it is up. Do show run, show IP route connected. All right, and it is connected. Okay. Now, it's showing up in my routing table. All right, now if I do a show run section BGP, I can see that I don't really have any network statements. Let me do a show IP BGP. I don't have anything in my BGP database. If I do a show IP BGP summary, do show IP BGP summary, I can see I'm not sending any prefixes. I'm also not receiving any prefixes from my peer. 0 is not bad necessarily. It means I'm not really routing anything with BGP, or at least exchanging reachability information with BGP. But let's go ahead and add, under the BGP process, router BGP 5.5, network 172.16. Now, this is where you have to be very careful. This is another thing that's unique to BGP that doesn't exist in the other IGP processes. Typically, we would be putting in network statements to identify which interfaces we want to initiate the routing process on. And on top of that, then that network would be included in the routing updates that are being sent to the peers. In the case of BGP, we're identifying what prefixes are going to be advertised in my NLRI. We're not enabling BGP on the interface, because that's not, BGP doesn't run on links. BGP is used to exchange routing information, prefix information. You also want to make sure that the subnet mask you specify for that prefix matches exactly with the prefix that exists in the routing table. In other words, in order for BGP to include a prefix in its updates, it has to match some sort of underlying IGP or connected or static routing process in the global RIB, routing information base. If I would have just put in wildcard mask, or supposedly a wildcard mask of 255.255.0.0 and a 172.16.0.0, that network would not have been included. All right. So if I do a show IP BGP, I can see now that that prefix exists in my BGP RIB. All right. I can see also that it is a valid path. It is the best route. I can see the default weight. We'll talk about that later. The multi-exit discriminator, the path internal, and the next hop attribute. So like I said, I see the prefix, I see the prefix length, I see the attributes. Okay? And it's pretty straightforward. Next hop of quad 0 means that I'm the originator of that particular prefix in the BGP domain. Now, if I go to router 4, router 4 should be learning this prefix from router 5. Do show IP BGP summary. I should see now that I'm getting one prefix from my peer. And if I do a show IP BGP summary, or do a show IP BGP, do show IP BGP, I can see that information. This is the attribute that's getting set by router 5 to indicate, hey, you need to come to 5.5.5.5 to reach that particular destination. All right? Now, this is being learned via an external BGP peer. We can actually tell that because this I here, the I means a couple of different things. The I here, which is the origin code, that's what we see in the last column here. We don't see the title. It's a little confusing. This I does not indicate that it's an internal route. This I indicates that it was learned through some IGP process. Okay? Interior process. If I do a show IP, eIGRP, topology, we can see that, because when I set up my eIGRP, I just kind of did a 172.16.0.0. So I'm learning this route through an IGP routing process, eIGRP in this case. All right. It's interesting, though, that we're not using eIGRP to reach this destination prefix. If I was, then I would see a RIB failure here, indicating that the route was not being installed. I'll see if I can demonstrate that in a little bit, but I would see a RIB failure here, indicating that I'm learning the route and using the route from a different routing source. So don't be confused here. This is the origin code on the end. If this was learned through an iBGP peer, that would be an internal route, and we would see the little I next to here. I'll see if I can demonstrate that towards the end. We're getting close, but we got a little bit more to talk about here. All right, maybe another 20 minutes or so. All right, and I'm kind of getting away from what I wanted to talk about, but let me go ahead and continue to kind of demonstrate this concept, because one of the things that I was mentioning is what's included in my update information. What information am I learning about a particular route? The prefix, the length, the attributes, and the next hop. Those are the three major components in the BGP database, which we can see with doing a show IP BGP. All right. Prefix, length. These are this is the AS path, which, by the way, is written in decimal format. That looks like a metric, but it's actually AS path. And we would probably want to change the dot notation just to make sure that we can see our extended or dot notation prefixes, or ASNs. All right. The bottom line is the next hop value is critical because, like I said, that's what BGP is going to use to do the route recursion process. Now, if I look at the routing table of router 4, if I do a show IP route, there's another thing that I want to mention here and show you. We can actually see the BGP route for the 57 subnet here. We're learning it through IGP. We're learning it through eIGRP. But external BGP has a lower administrative distance than eIGRP. External BGP has an administrative distance value of 20, whereas eIGRP has an administrative distance value of 90. So even though we're learning about the 57 prefix through eIGRP, we're using the BGP network layer reachability information. Notice what we see for these routes here. Next hop, which we see here as well, exit interface. Notice what we don't see in a BGP route. We don't see an exit interface. Okay? That's because BGP doesn't route to interfaces. BGP advertises network layer reachability information. So there's a recursion process that we have here that says, okay, the next hop is 5.5.5.5. So if I do a show IP ceph 5.5.5.5, that's where I can identify what interface I'm going to use to reach that particular next hop. Without learning 5.5.5.5 through the eIGRP process, the 57 prefix would not be reachable. Okay? It's much different in the case of BGP with as opposed to an IGP. IGP has to be able to perform some sort of recursion, otherwise that particular prefix or that route cannot be used. All right? If we advertise a route into BGP, but the result is a failed next hop recursion process, the route ultimately is not going to get installed in the RIB and it's not going to get advertised. Now, why do we care about this? Well, specifically in this case, what I'm talking about is the next hop. Why do I care about the next hop? Because we have different peering rules and different next hop process rules based on the different types of peers, whether it's iBGP or eBGP. All right? When we make a decision to route, when we make a decision to route two peers between different connected interfaces or loopbacks, that could possibly affect their traffic flow. In iBGP, it's a lot different. So let's actually see what that looks like from the perspective of router 2. So I'm going to add router 2 to this BGP process. We've got a loopback on router 2. Let me put that on here, 2.2.2.2. And we're going to set up an iBGP pairing relationship between router 2 and router 4. All right, so let's go to router 4 first. And we'll do router BGP 4.4. Oops. And we're going to say a neighbor. We'll go ahead and peer to the loopbacks. 2.2.2.2. Remote AS 4.4. And we'll also say neighbor 2.2.2.2 update source loopback 0. And let's go into router 2. Config T router BGP 4.4. These are internal BGP peers, so they're going to have the same ASN. Neighbor 4.4.4.4. Remote AS 4.4 and neighbor 4.4.4.4 update source loopback 0. All right, now we're not going to be able to establish an adjacency here. I don't know if we really call it an adjacency. I guess you can call it an adjacency. We're not going to be able to go into an established state, because if I do a show IP ceph for 4.4.4.4, no route. All right, so let's do this. Router OSPF1 network 172.16.24.0. and network 2.2.2.2. We have to establish some sort of underlying IGP reachability. Router OSPF1. Network 172.16.24.0. And network 4.4.4.4. All right, so I should be able to ping 2.2.2.2 as soon as I get an adjacency. I messed something up. Show IP OSPF interface brief. Gig 02, that's correct. We're in a wait state. All right, probably just need to wait. So show IP OSPF interface brief. Now we're still going through the process of negotiating the peers. We're not full yet. Not sure why it's taking so long in this case. There we go. All right, so let's do a ping to 4.4.4.4. All right, do show IP BGP summary. Now, we should establish an adjacency. There we go. And we are getting a prefix. Okay, and if I do a show IP BGP, I can see that the prefix is 57. So I'm getting this prefix. This 57 network is being sent by router 5 over to router 4. We now have an iBGP peering relationship between 4 and 2, and we're sending that route from one iBGP peer to another iBGP peer within AS 4.4. Okay? All right. Now, in the case of iBGP next hop processing, the next hop value does not get modified. This has to do primarily with the concept of route reflection, where you typically would not want the route reflector to be as a part of your data plane when you're doing your packet forwarding. All right, it's essentially only the box that hosts the control plane information. The idea is that we're trying to cut down on the control plane load, but this comes at the expense of having a detailed view of the topology, if you will. All right, so you could have some sort of ASR in your network that doesn't want to process all the data plane traffic, but it does contain the hundreds of thousands of control plane reachability information. All right, there are advantages, but there are also some different design implications to this concept. In most designs, you don't want the route reflector in the data plane path. In our particular case, router 4 would have to be in the data plane path because it's connected through to router 5, through those two connections. All right. The problem is, in this case, though, from router 2's perspective, if you look at the BGP database, we see that it is a valid route, but we do not indicate whether or not it's the best route. And that has to do with this next hop attribute. That was the attribute that was set by the eBGP peer to router 4, which was router 5. And that attribute was carried forward over to router 2. Now, if I do a show IP Ceph to 5.5.5.5, I have no route, which means essentially I have no reachability, which means the route cannot be installed. All right, if I do a show IP route, I don't see the 172.16.57 prefix. And I'm running OSPF in this case. I'm not redistributing into my IGP. So I either have to have some sort of reachability to 5.5.5.5, which is typically not going to be the case because that's inter-AS routing, or I have to modify the next hop attribute by changing the next hop processing rules by the reflector, in this case router 4. All right, now you could do this a couple of ways. We could do the next hop self command, which I'll demonstrate in a second, or we could do some sort of like route map action set IP next hop, which I'm not going to demonstrate. We might do that in one of our more advanced discussions. So I'm going to go into router BGP 4.4, and I'm going to say neighbor 2.2.2.2, and whenever I send any prefixes to 2.2.2.2, I'm going to establish myself as the next hop. Remember, this would not apply to iBGP prefixes, because iBGP routers never reflect iBGP routes learned from other iBGP peers. So this is only going to apply to overriding the next top attribute for the eBGP process, the prefixes I'm learning through eBGP. Notice what happens on router 2. If I do a show IP BGP, I might have to clear the, we should see, yeah, let's just do a quick clear. All right, we should see in this case, once we get the prefixes back, I probably should have just done a soft reset, but once I get those prefixes back, we now see that it is a valid route. Not only is it a valid route, it's being learned through an internal BGP routing process, not an external BGP routing process. By the way, again, do not confuse this I with this I. Origin code is at the end. This is a route that's learned through iBGP, IGP, EGP, or through some sort of aggregate address or summary option, right? Incomplete means we're learning the route through some sort of route aggregation process. All right, now if I do a show IP route, we can see that the BGP route gets installed and it has a administrative distance value of 200, which is typical for iBGP. It's default for iBGP. Keep in mind, we don't really want to trust iBGP routes over IGP routes. But because we're running a separate autonomous system, OSPF as opposed to eIGRP, we're going to go ahead and insert the BGP route. In iOS 15.1, I don't remember the specific, 15.1.1 or something like that, you can actually do the next hop self command for all the routes, meaning that you're actually going to insert the route reflector into the data plane path for every single route that goes into the process. All right, now there's some other implications to this process that you need to understand. And it won't really work in our topology here because there are some design implications for making yourself the next hop for that particular prefix. You're better off redistributing those external prefixes into some sort of IGP, like sending it into OSPF, and then allowing OSPF to define that reachability, as opposed to making sure that that route gets exchanged through iBGP. But you might have some other autonomous system number attached over here to router 2, and you're acting as a transit AS, and you want to be able to route or advertise that information across your AS. All right. It's much better to go ahead and send the routes into your IGP. In the case of eBGP, we do change the next hop value because essentially I'm assuming that, hey, if I'm advertising the route to you and we're external peers, you don't know the details of my topology, so I have to give you the route and then you have to send the packet to me so I can make the routing decision. All right? Now you could configure something called third-party next hop. Same concept with eBGP peers. You can do a set IP next hop using a route map action. You can do neighbor next hop unchanged on the eBGP peer, but that's a very limited use case as well. In fact, the only time you might want to use this is like DMVPN phase 2, where you had, like eIGRP and OSPF, we were worried about the route reflector taking over the next hop information for spoke-to-spoke communication. So if we're running eBGP peers over DMVPN, that would be kind of your use case scenario in that particular case. We want to point the route to the remote spoke, not the hub in this case. eBGP neighbors normally should set the next hop to itself though. All right. R4 and R5 are peering in this case. We've already established the peering relationship between R2 and R4 as well. We'll get into some more details, but you always want to be able to check the recursion process. That's very, very important. Now, what happens if, let's see if we can break this, right? We know the eBGP administrative distance is 20, right? And we know that we've got this 57 prefix now being propagated from router 5 to router 4 to router 2. If I go into router 2, I should be able to ping to 172.16.57.5, and I have full reachability. I can even source that from source loopback 0. And actually, I won't be able to source it from loopback 0 because router 5 does not have any reachability into AS4. And that's because we didn't do, first of all, we're not advertising those prefixes in BGP. And secondly, I would have to do a next hop. Well, actually, no, I wouldn't have to modify the next hop because 5 would be getting that from an eBGP pairing relationship with 4. All right. But the idea anyway is that we're looking for that greater than symbol. Let me show you again. Do show IP BGP. We're looking for that greater than symbol because that tells me that I'm going from the BGP rib to the global rib to the fib. All right. And that we have full reachability based on the next hop attribute. And because this is a iBGP route, we have that internal status code again that's right next to that greater than symbol. All right. So if we look at the route descriptor block for the destination prefix, I showed you this already, right? With BGP, there is no exit interface defined in the route descriptor block. So we have to do this recursive routing lookup where we're now relying on the underlying IGP for reachability. And that's what that recursive process is. And you can see that in the forwarding information base. If I did a show IP Ceph for 172.16.57, I would see that there is a, we're using ECMP. Well, from the case of router 2, we're just simply going out of gig 02 to get to the destination. All right? All right. If I made a mistake, I could introduce something called a race condition into BGP where we cause essentially an infinite recurring loop in the BGP process. So let's try and do that. I don't know if I'm going to be able to accomplish this, but let's give it a shot. We're almost done, guys. Hang in there. We're just about done. Let's do a debug IP routing, because this may be a scenario that you see in the troubleshooting portion of the exam, where they've introduced some sort of race condition in the BGP process, and you have to identify what that condition is and why it's happening. So let's go to router 5. And we're already in the BGP process. Let's go ahead and advertise the prefix. This should do it, actually. Advertise the prefix we're using as the peering address into BGP. So let's do a network 5.5.5.5 mask 255, 255, 255, 255. Now, what I should see, if I'm doing this correctly, yay, it worked. I should start to see these recursion errors on router 4 saying, uh-oh, there's probably a routing loop because I'm trying to get to 5.5.5.5 and I can't get there anymore. All right? It kind of makes sense, right? If I do a show IP route BGP, show IP route BGP. Oh my gosh, come on. Try this again. I'm learning 5.5.5.5 through BGP, but I'm trying to establish a peer to 5.5.5.5 with BGP. So why did this happen? Well, it happened because eBGP routes have a lower administrative distance than eIGRP. Now, they don't have a lower AD than static routes, but because we were using eIGRP to demonstrate reachability or to advertise reachability for those loopbacks, the eBGP route would take precedence over the iBGP route. If I do a show IP route 5.5.5.5, it says, hey, you want to get to 5.5.5.5, go to 5.5.5.5. That's not really going to work. Okay? I'm going to go to 5.5.5.5 to reach 5.5.5.5. All right? So the router's reporting a loop. That means I essentially cannot install the route into the table. The BGP pairing process is going to continue to go up and down. this is where the race condition comes into play. Sometimes I'll be peered, sometimes I won't be peered, but I'm certainly never going to be able to route. If I do a show IP BGP summary, you'll notice here that I'm seeing two prefixes, right? So it shows the adjacency is up, but I'm not going to be able to route. And eventually that will go down, and it will probably come back up. Oops, there we go. I haven't seen it go down, but it ain't good in any case, right? So it looks like it's kind of adding eIGRP, and then it's taking away eIGRP, and it's adding eIGRP. There's a bunch of weird things happening here. All right, see, it's deleting the routes, the BGP route, because we lost our adjacency, and then it's adding the route with eIGRP, and then we should see it delete the route through eIGRP, updating BGP, closer administrative distance for 5.5.5.5. So now I'm flushing out those two ECMP routes that I got through eIGRP. And we're just going to keep going through this process. So you might see something like this in the troubleshooting section or the diagnostic section of the lab. Would be a really difficult thing to figure out if you weren't familiar with, you know, administrative distance values and how next hop values work and exchanging information works. There is a way that we could fix this, and they may actually make you fix it this way rather than take out the network statement. They say, without taking out the network statement, go ahead and fix this particular problem. Well, we could do that by simply changing the administrative distance of eBGP. So if I go into router 4 and I say router config t, router BGP 4.4, and I say distance BGP, and we'll just do 91. 91 is the internal, right? Or external, excuse me. Then we've got our internal. We'll leave that at 200, and then we've got our local. We'll go ahead and leave that at 200 as well. All right. So the routing loop should disappear now. All right. Eventually. I may have to clear the BGP process. Let me do a show IP route 5.5.5.5. So it's still getting it through BGP. Still has a distance of 20. That should not be the case. Let's do a clear IP BGP star. All right. I could probably wait for that to change, but I'm not patient enough. Let's do a show IP route. And we're back to eIGRP. Okay. So that means that eIGRP, let's do our undebug all as well. eIGRP route's going to take precedence because it has an administrative distance of 90 versus 91. The route's shown as being installed by eIGRP. Now, how did that affect BGP? If I do a show IP BGP 5.5.5.5, we can see we have an entry for that route, but we're getting a rib failure. All right. In fact, if I do a show IP BGP, you can see it here as well. We're actually getting a rib failure from both. Yeah, well, that makes sense actually. The 57, again, this is not something that would typically be the case. 57 prefix is included in the eIGRP, which means we're essentially learning this through the eIGRP process. So rib failure is not necessarily bad. That means BGP is accepting the route. It's just not being installed in the BGP rib because we're learning about that prefix through another process that probably has a lower administrative distance or something like that. Okay. All right. And that rib failure would continue on down the line to the rest of the destinations. All right. I think that's about it for today, guys. Let me think. Oh, I do want to mention one more thing here. These numbers here look the same. It's a little confusing. This is the next hop. This is the router ID. In the parentheses, you see the router ID. It happens to be the same because it's a loopback, but those numbers don't necessarily have to be the same. The numbers prior to the parentheses is the actual next hop attribute, and then the 5.5.5.5 in the parentheses is the router ID of the peer. Okay. All right, folks. Any questions before we wrap up today's lesson? All right. What I'm going to do, let me stop the video here. See you guys in the next one.